Good morning. Today we're going to talk about alternative flash chromatography media. These are chromatography media that are other than silica gel, although we will discuss new and different ways of using silica gel. We will also discuss C18, although that's not really considered an alternative media. We will discuss different ways of using C18 to expand your chromatography repertoire. The reason that we use what we term alternate media is that we would then see different column selectivity, that is the elution order for the peaks. We would use alternate media for delicate compounds that decompose on silica. And some of these media are reusable so that you can use the columns over and over again. By alternate media, we mean columns such as aluminum oxide, Diol, Cyano, and Amine bonded phases. We're going to start off with reverse phase. We mentioned the different types of columns over here. Very polar media include alumina and silica gel. Less polar are amine, diol, and cyano, and finally C18. We're going to start off with some basics. Reverse phase solvents are more polar than the column. So running C18, water methanol, water acetonitrile are more polar than the C18. So that's reverse phase. We have several types of C18. RediSep RF C18 is a good general purpose silica with irregular particles. It is not end-capped. The gold C18 is used for higher resolution. It has spherical particles, so they pack better. They're smaller particles and they're end-capped. And the gold C18AQ is used for running compounds that elute in a lot of water, highly aqueous mobile phases. It's resistant to phase collapse. What I'd like to discuss is non-aqueous C18. Use a RediSep RF gold C18. The water is replaced with a alcohol. You can use acetonitrile. Solvent B is a less polar solvent, such as dichloromethane. It's less polar than solvent A, and so it's still reverse phase. It must be miscible. Useful solvents include acetone and dichloromethane. And extreme cases, you can even use hexane. These solvents often absorb UV, so you can use the all-wavelength collection feature on your CombiFlash system. And it's very useful for very nonpolar compounds. In this case, lycopenes were purified on a torrent, a very large column using non-aqueous C18. You can use the C18 TLC plates for method development and determining which solvent system works best. In this case, we're interested in the large peak. And by HPLC, you can see that we purified the lycopene essentially pure. The solvent system over here was methane and dichloromethane, and the lycopenes absorb at 450 nanometers, so it was well away from the dichloromethane absorbance. Going to the other extreme, from very nonpolar samples to very polar samples, we have the RF gold C18AQ. This C18 is less susceptible to what we term phase collapse. Under highly aqueous conditions, less than 5 or 10% organic solvent, C18 has a tendency to self-associate, where the C18 chains associate with each other rather than the solvent system and the sample. One symptom is chromatography that is irreproducible. It doesn't repeat itself. You also get improved retention of compounds under highly aqueous conditions. In this case, we have a couple of dyes, and using the RediSep RF gold C18, the first peak elutes at the void volume, and the second peak elutes at about 8 minutes. Using the C18AQ, the first peak now is retained somewhat and elutes somewhere after the void, and the second peak now elutes at about 10 minutes, so there's improved retention. And in fact, the first compound, the tetrazine, it allows some purification to be made on that molecule. Other uses for the RediSep RF Gold C18AQ is desalting or desolvating. I had a problem where I was running a natural product, epicatechin gallate, and I did the NMR and DMSO D6, and I needed to remove the DMSO for further work. So I used a small C18AQ column to remove the DMSO and elute the compound in methanol, which is a lot easier to evaporate. Going on to the alternate media, as I call it, we have a Diol column. It generally runs as a normal phase column, although there are exceptions. It's less polar than silica, and it's useful for less polar compounds. You might recall from your organic chemistry that the diol can act as a protecting group for ketones, and it can also react with primary and secondary amines. This usually happens if you add an acidic modifier to your solvent system. I haven't had any issues with ketones running without modifiers using this column. Diol method development, you can use a TLC plate. We have matching TLC plates for method development. And to get an estimate of where the compound elutes, the 1 over the RF tells you the column volume. And by running a variety of compounds, we can predict the actual retention time, with the exception of some xanthine alkaloids. Theophylline eluted later, but it did elute from the diol column. Here are some more examples with other compounds as well. And again, the xanthine alkaloid eluted later than expected. However, it still came off of the column. One place where the diol column was very useful was for a delicate compound. We synthesized transanethol oxide, and with the epoxide group on it, the compound can't be purified on silica. Silica catalyzes the opening of the epoxide ring, and the compound just doesn't dilute because the open ring then reacts with silica, and I've essentially functionalized my silica with my product here. However, using the diol column in normal phase, I was able to purify the compound, and I found the major peak over here contained my compound, and I was able to get 68% recovery or yield from the reaction. I mentioned earlier that diol runs sometimes as reverse phase, and here's an example. I'm using the Brilliant Blue dye again. It's a very polar molecule, and this chart over here shows that as I start off with 100% acetonitrile and I increase the concentration of water, the elution time decreases. So the gray area, the compound is running as a reverse phase column. As a normal phase column. Then, after about 50% water, as I continue to increase the water, the compound elutes later and later, and the column is now acting as a reverse phase column. So the gray area is an example of what we call HILIC, hydrophilic interaction liquid chromatography, also known as aqueous normal phase. So the next question we have is, does this column always act in this fashion? And I have over here a sample of butylparaben, and in this case, the column acted solely as reverse phase. It did not show any normal phase tendency with a nonpolar compound. So polar compounds, the diol can act as normal phase or reverse phase, with the changeover happening at about 50% organic solvent. With a nonpolar compound, the diol column acts solely as reverse phase. The amine and thiol columns can also show normal phase and reverse phase chromatography. The amine column that we will discuss later, I expect it to behave similarly to the diol column. And the cyano column, generally, I expect the changeover to happen at about 50% organic. And I expect that for nonpolar compounds, it will also act generally only as reverse phase. The amine column contains a basic group on it. It is useful, again, for normal phase or reverse phase. It is particularly useful for basic compounds. The media itself is basic, and therefore no basic modifiers are needed. It may act with aldehydes or ketones to form imines, and after you run the column, you wash and store it in 2-propanol. The diol column also gets washed and stored in 2-propanol as well. By storing these columns in 2-propanol, you prevent the column body from swelling up and the packing from getting loose, particularly with normal phase solvents such as hexane or ethyl acetate. Amine method development, you can use normal phase solvents, and the polarity is similar to diol. Over here, again, similarly, we can predict the retention time from the matching TLC plates. And we have good agreement between the predicted retention and the actual retention. And here's an example with some alkaloids. The blue trace shows silica gel, and I can resolve caffeine and thiopurine, and I could get pretty good resolution, not quite baseline resolution, with a 1% load on silica gel. However, if I go over to an amine column, I have a large amount of resolution, and I could do a 10% load. What that means is I can do the same thing in a single run with an amine column as it would take 10 silica columns to do. So it saves a lot of time. And furthermore, you can see that I have a huge amount of resolution over here. What that means is that my compounds are actually more pure than I would get off of silica gel. The solvent system in this case was dichloromethane and methanol. The cyano column runs normal phase with organic solvent, and it is generally reverse phase in aqueous solvents. We do not use matching TLC plates, but you can use a small column for method development. And here's an example again with this epoxide that we discussed earlier. It was eluted in hexane and ethyl acetate. Again, the epoxide decomposes on silica. The cyano column is reusable, so after you get done using the column, wash the column and store it in 2-propanol, because the hexane and ethyl acetate will cause the plastic column body to swell up. Another alternative media is aluminum oxide. Like silica, it is generally considered a single-use column, and we have it in 3 forms: acidic, basic, and neutral. It's a normal phase column, and it can be run with either methanol or water, and we have matching TLC plates for method development. As an example for alumina, we have a petroleum sample. The compound is a ionizable compound purified from a strong cation exchange column, and the chromatogram came off of basic alumina because the compound is basic, and we were able to get a peak that was fairly pure off of it. RF gold silica can also run in very highly polar solvent. It can run in methanol and water, and here's an example: purification of caffeine and adenine. I apologize, some of these slides, I'm not quite sure why some of the things are overlapping here. But the experiment over here was run in dichloromethane and methanol, and the adenine elutes at about 40% methanol. And as long as we keep the solvent system neutral or acidic, the silica does not dissolve in methanol. We use a very high purity silica here, similar to what is used for the HPLC columns used for HILIC. So as long as you keep the solvent system neutral or acidic, you don't have to worry about silica getting into your sample. Here's another example with HILIC, aqueous normal phase. That's the term used in older research journals. Solvent A for HILIC is usually alcohols, methanol, ethanol, acetonitrile, acetone, or THF. You start off with about 2% B solvent, which is water. If you need to add a modifier, you would add something like acetic acid, formic acid, or trifluoroacetic acid. In this example, purifying some vitamins, the three compounds are well resolved on silica HILIC, and they are not at all, two compounds are not resolved on C18. The other thing I find with HILIC is I find it best to start off with a solid load cartridge and dry the sample onto the solid load cartridge rather than do a liquid injection. These compounds being water soluble, they tend to run down the column very quickly if they're dissolved in water, whereas with the solid load cartridge, it allows me to get very good resolution. Other columns that act as HILIC include Diol and Amine, and here's our a dye that we purified using a Diol column, starting off at 2% water and going up to about 50% water, and you can see that we purified the dye very nicely from some very minor impurities. So in any case, that's our rather short presentation over here, and now we'll open the field to questions. Does anyone have any questions, please? Good morning, Peter. Hi, how's it going? Okay, the first question we have is an increase in load in amine relative to silica a general expectation? The answer to that is no. The reason why I have an increase in load with amine is because the amine column had a different selectivity for those compounds compared to silica. With the different selectivity, that caused an increase in resolution in this case, and that allowed me the greater load. The selectivity of a column, I don't know how to predict it a priori. However, what I can do is run a TLC plate and compare whether I get an increase or decrease in resolution. And with an increase in resolution, that allows me a larger sample load. Another question is synthesizing isoquinoline alkaloids, and the question is, would I recommend the amine column? It is something that you can certainly try. Instead of buying the column initially, you can purchase some TLC plates to see if the TLC plate, if the amine functionality will work for you, and see if the resolution is improved. And you can also try different solvents on the TLC plates. Let's see, how do you develop alumina-based separations? I find the TLC plates to be very unpredictable of column separation. Should we oven dry our plates? I find that the compounds I find that TLC plates are actually pretty good. What I also find is that there's some certain ways of running TLC plates that improve reproducibility. The first thing that I'd like to do with TLC plates is saturate the atmosphere in which I'm running the plate first. So I would get a TLC chamber with a good fitting lid so that the solvent can ventilate out. And I would mix up my solvents and shake up the chamber first and then prepare my TLC plate. This allows the atmosphere to become saturated, and it greatly improves the resolution, the predictability of TLC plates. Look for an application note from us sometime in the future about that, because I find that people have made the same comment, and I've worked with customers for techniques to improve the predictability of TLC plates. Will these slides be made available? Yes, we can make them available. Another question is, how many times on average can one reuse the amine columns? The amine columns can be used at least 10 times. However, there's a few precautions to worry about. One of them is store them in 2-propanol after you're using them. The amine column is fairly basic, and by storing them in 2-propanol, you're reducing the possibility that the amine column kind of eats itself. Silica dissolves under basic conditions, so the amine functional columns do have a bit of a lifetime. But I've kept the columns stored in 2-propanol, and I've been able to use them after a year and still get good results. One other thing I neglected to mention with the amine column is absolutely do not use an acidic modifier. The acid has an anion in it, and if you add an anion to the amine column, you've converted it to an ion exchange column, and it won't work anymore as an amine column. Can one do soft media flash such as DE, AE, Cephalodex, and also Chiral flash? You certainly can use Cephalodex on our columns, and we have an application note where I've run Cephalodex LH20 on our system. I think we have your email address, and we can send you a link to that application note. Which column do you recommend to purify very polar compounds such as imidazolium salt and what solvent? My very first guess on that one is I would try either the silica. I'd start off with silica because those are usually lying around everyone's lab. And again, not every silica is amenable to aqueous normal phase, but I've tested our RediSep RF Gold silica, and it doesn't bleed silica. I would start off with the silica gel, and I would start off with, say, water methanol or water acetonitrile. And if I need a modifier, I would go acidic. After that, my next choice would be the Diol column. Any other questions? If you have any further questions, you can send us an email, and we can answer them privately as well. We'll give you another minute or so to come up with any more questions, and I thank you very much for your time. And it's been a pleasure working with all of you today. Oh, here we go. Can you estimate mobile phase for alumina based on that for silica gel? The answer is no, not really. The reason for that is that the columns do have different selectivity. When I worked in natural products over at Merck, I had one example where a compound would not work with silica gel at all, but it eluted from alumina with 100% methanol. It was a cyclic peptide. Likewise, I find that silica tends to work very well for extremely nonpolar compounds, such as those found in the petrochemical industry. Okay, so with that, we'll end this. Oh, I'm sorry, one more question. What do I recommend for purifying two compounds that have very close RF values and very hydrophobic to run on silica? Very close RF values and very hydrophobic. That's depending on the cause of why they're so closely related. My next choice would be trying C18 because C18 is often good for resolving closely related compounds. And after that, very hydrophobic, I would try aluminum oxide. And then after that, I might try, say, the cyano column. That would be my, that would be what I would try in roughly that order. Okay, thank you again for your time, and it's been a pleasure answering your questions.